Round 2. This is Exam 5 review. And on chapters 27, 28, 30, and 31. So these will be the final chapters for the course, as I've already done all the chapter lectures. We have all the labs completed, and then I'll be dropping the lowest lab test score. And I will not be doing any kind of review for the final. So the final will be comprehensive, and we'll go from there. So it'll be the same format as the other exams. Okay, so going from there. All right. All right, so chapter 27, I'm just going to review the sections again, and this is on models of the atom. So to review quickly as far as that, just going through sections, just 27.1, properties of electron. Uh, 27.2, and this also deals with the lab, is on black body radiation. Basically the graph we have of intensity versus wavelength, right? As far as how that goes. And then the fact that the peak wavelength, lambda p times t, is basically is 2.9 times 10 to the minus third. So what this means is, as the temperature goes up, the wavelength goes, the peak wavelength goes down, as far as that's concerned. And also the fact that the power radiated is proportional to the temperature to the fourth power. And this is in degrees Kelvin, and this is in meters. So the power is proportional to the fourth power. So you double the temperature, and the power radiated goes as 2 to the fourth, or 16. So that's that part. Also part of this section is the Planck's constant. H, which is 6.634 times 10 to the minus 34th. And related to this is the energy of a photon is H times the frequency. So that's Planck's constant to explain black body radiation theoretically. And so this is a constant here, this is the relationship here, and this relationship. So these are the important relationships there. All right, so that's the first two sections. Okay. All right, moving on. All right, we already talked about 27.3 is again talking about energy is H times the frequency, and this deals with the photoelectric effect. All right, so again, if you have some kind of light with some energy based on the frequency on a metal, and emits, it hits a electron goes out, and it does not matter on the intensity, but as I said, it matters only on the energy. So no matter how bright it is, if it doesn't have enough energy, it's not going to excite that. So this is what Einstein, one of the things he got his Nobel Prize for, as far as the photoelectric. And we had the lab, again, dealing with that. I believe it was lab 12, with that issue there. Okay. So this all deals with the concept of light being made up of photons. Right, so these are particles, which also have a wave nature to them. All right. 27.4, while we're on that, on protons. So photon is a particle with this energy, but it also has a wavelength given by and so it has a momentum. Remember, momentum is mass times velocity. But for a photon, mass, there's no such thing of, so this is momentum. And classically, momentum is mass times velocity. However, for a photon, the momentum, since it has no mass, massless, I didn't get into this before, because the speed is the speed of light, the energy is actually E divided by C. And this wavelength is then given by H over lambda. So a photon has a momentum given by H over its wavelength. So it has a wave nature to this. And this is how a photon has a wave nature to it. So you get light, we get diffraction. We had the diffraction interference lab from before. This is explained in this way. All right. All right, so this explains, so then we explain 27.7 deals with this in more details. Wavelength is given by H over P. So if you have the momentum, so again, H is Planck's constant, P is the momentum, that's the wavelength, and we dealt with the electrons have wavelengths on the order of 10 to the minus 10th meters, all right, which is in the order of X-rays. But say a moving object, classical objects such as a bowling ball, still have a wavelength, but it's on the order of 10 to the minus 34th meters, which is incredibly small. So when you get to very tiny particles, wavelength is on the same size as the atom. So that's how we end up with electron microscopes, electron diffraction, and things like that. But for classical particles, like, throw this thing, it has wavelength with this momentum, but it's so incredibly small, it's immeasurable. So that's part of 27.7. Okay, this also deals in electron microscopes. Is a little bit on 27.9, although we're not going to deal with that per se. Right? So that's that section. Okay. All right. And then moving on from there, we have 27.10. Early models of atom. Okay. And the Bohr model, I'll just deal with that primarily, where you have proton in the center, and this is 4 hydrogen, and electron shells orbiting at sort of what we call that. And the way we see either emit light or give out light is by a transition between one layer and another one. And we have then this explains spectra, 2710, 2711, right? Emission spectra. That's how each element has unique spectra, as we talked about before, and as the lab we did on that. And the fact that the wavelength for the hydrogen atom, the Bohr model, is R times 1 over N minus 1 over N squared, and N sub I is either 2, 3, or 4. Oh, 1, 2, or 3. 1, 2, or 3. I mean, you can go higher, but the main ones are, this is the Balmer series. As we said, this is visible, UV, and infrared as far as that's concerned. So this is the first one that was visible. This is what we did in the lab. And this is the Rydberg constant, which we talked about already, right? So this is what it starts from. So the transitions are from higher states, so it's 1, 2, 3. If it falls from a higher state to lower state, it's going to emit light. If it absorbs a photons, go from lower state to higher state. This is what we did in the lab. So this is part of the lab. This is also deals with the Bohr model, 2712. As far as that is concerned. And that is chapter 27. Okay? All right, chapter 28. First section 28.2 is just wave nature of what electron, which we've already talked about. All right. And then 28.4 is Heisenberg uncertainty principle. Meaning because of the fact that you're using all right, because you're using photons to measure where a electron is located, and because they're basically on the same size, then there is an uncertainty of where it is based on h over 2 pi is going to be less than or equal to the uncertainty in the position times the uncertainty in the momentum. Meaning the better we have its accuracy where it actually is, the more uncertainty we're going to have in its speed. Because you hit it, it's going to affect where it's located. So this only deals with small particles. So let's say electron, we talked about this before. So that's Heisenberg uncertainty principle. We also have it in terms of energy. So this is also the change in energy, uncertainty energy, times the change in time of that. Okay, so this is all part of quantum mechanics. It's basically we cannot be absolutely certain where particles located. Could then you can predict it for all, theoretically, for all time, exactly how everything would interact. And that's not the case. So that's basically what quantum mechanics is. It's not certain. Okay. All right, the rest of this chapter basically deals with the quantum mechanics, basically the structure of the periodic table. So moving on from there, again, we have 28.6 and all right, 28.6, 7 and 8 deals with quantum numbers. And L, M sub L, M sub S, N sub S, and the rules related to this. Okay, we talked about this already for chapter 28, and basically the exclusion principle, which we talked about. And this means that no two electrons can be in the same state. So again, if we have, hydrogen has one electron, helium has two electrons, one spin up, one spin down, and that's a filled shell. The next one, lithium, has to go into a new shell, and that's where we build up the periodic table based on the fact that in a particular atom, no two electrons can be in the same state. So that's how we fill up the periodic table, the rules for how these numbers work. And as far as that's concerned. All right. Then we had 28.8 also talks about electron configuration. So we also have problems with that. Right? How does that, the rules for that apply? So for hydrogen, it's 1s2, 1s1. Helium is 1s2, and then it's filled. Okay. For lithium, it's 1s2, and then 2s1, and so on. And how that fills up, once those are filled, then the next step, we go 1s2, 2s2, 2p1. So that's for the fifth element, which would be boron, and go from there. So part of the test will be given an electron configuration, what element is it, which ones are possible, using these rules, and the fact of chemistry deals with SP, D, F, and so on. Okay, and then what those go as. All right, and that is chapter 28. All right. So this is how the periodic table is developed and why it exists as it is. Okay, we're skipping chapter 29, even though I have it listed. So the next chapter is 30. Okay, and 30 and 31 deal with the nucleus. All right, chapter 30, 27, 28 deal with the electronic structure, how electrons configured. This is part of chemistry. Chapter 30 and 31 deal with properties of nucleus. So we're dealing strictly with the nucleus. Okay. And in that case, okay, we have atomic number, all right, number of protons, Then we have mass number, which is number of protons plus neutrons. Okay. And that, and the fact that the radius of the nucleus is approximately 10 to the minus 15th meters. Compare that to the radius of the atom itself, is about 10 to the minus 10th meters. All right, this is 100,000 times, which again explains why most of the vast majority of the mass is in this extremely small nucleus. Okay, so that's that part. We got into binding 30.2. Binding energy a little bit. All right. And we'll get into this in this graph of binding energy and mass number A. So this is A and this is Z. All right, so Z is an atomic number, A is the mass number. All right, how this graph does this, and it peaks at iron 26. But we'll save that more for chapter 31 as far as that's concerned. Okay. The rest of this chapter deals with radioactive decay. So again, starting with 30.33, 34, 35, and 36. All right, this is alpha decay. Okay, all right, properties that lead to that, which again is a helium nucleus. Beta decay, which is an electron, and the kind of reactions that are alpha decay, like decay of uranium, beta decay, like decay of carbon-14, and then gamma, which is strictly based on, this is a photon, we use a gamma because it's a high energy photon. The types that lead to this of reactions, nuclear reactions for each one of those. And then 30.8 is dealing with radioactive decay, and that change of N is some decay constant times what we start with times change in time. So what this leads to is an exponential decay, as we talked about. Okay, so this is what we start with, and this is time, and this is E, this graph is e to the minus lambda t. And based on that, we end up with half-life. We define half-life as lambda is 0.693 over t to the half. So this is terms of half-life. So to me, if this is, whatever the unit this is decay constant. Whatever units this is in, it's going to be in the same units. So if it's in seconds, it'll be in seconds. If it's in hours, it'll be in hours, and so on. So this will be in time. So this is a unit of time. And this is in unit of time to the minus 1. Okay. We talked about half-life of different samples. So uranium 238 has a half-life of 4.5 times 10 to the 9th years. we have carbon-14, which is half-life of 5,760 years, more or less. And then you have others are much smaller. The ones that are extremely tiny, the half-life's on the order of microseconds or less. So this is that part of the graph, what we're doing in the lab. And this also deals with decay series. All right, so what kind of reaction occurs? We talked about that. And then 3011 deals with radioactive dating. And the use of that. The fact that this is for dating rocks. Because it lasts, rocks, Earth's been very old. And this is for once living things. Okay. So that's chapter 30. Okay. All right, then chapter 31, which is again the final chapter for the semester. Okay, so this is all just radioactive decay. And chapter 31, all right, deals with fission. And this deals with the fact of the example of uranium. Again, 1 neutron plus uranium-235. Instead of decaying, it emits barium. And I'm not going to get into details of that. Krypton plus 3 neutrons. So this ends up a multiplier there. You get one uranium with one atom of uranium with 1 neutron, it breaks down, emits 3. So multiplier effect, so this ends up with a fission reaction as long as you have a critical mass. So this can occur, but you have to separate U-235 from U-238 because U-238 does not undergo fission. Does not fission well. Does not fission easily, let's put it. All right? They have to set, and that's what was the whole basis of the Manhattan Project. And again, this is instant, which is how the atomic bomb was able to be developed. So that's fission, as far as that's concerned. Get into nuclear reactors, you get into that part, and then 31.3. So that's fission, it breaks down. Fusion, on the other hand, 31.3, fusion, roughly, all right, you end up with hydrogen 4H combined to make 1 helium atom, of which weighs, this weighs more than that, plus energy, depending exactly on the reaction, based on the principle of E equals mc squared. So the extra mass, so this weighs more than that, so that the extra energy, extra mass converted energy from m equals mc squared. Okay, so this is fusion. And this works again on the binding energy graph we had before. This keeps going and it peaks at iron 26. So this is the limit of, so for this part, this is fusion, as we said. This part here can be fission. Now, radioactive decay could occur anywhere on here. So this is, again, the mass number A, and this is energy. So it peaks here. So if you have it in the sun, this is what goes on in the sun. And if the star is big enough, it can fuse higher and higher and higher until it reaches iron. Iron cannot do any fusion. It takes more energy to combine it than it does to split it. And so in that case, if this occurs in a star where the core turns iron, it becomes a supernova because it collapses. So this is part of that basis and parts. All right. And then the rest of the chapter deals with biological effects. Okay, and talking about alpha radiation, what's the danger of that? Beta alpha, which is that decay, beta decay, and gamma radiation. These are the kinds of nuclear radiation we have. Which ones are the most dangerous? How do we measure that? So this is part of the effects of that. And this, there's also, we're not going to get into it, but there are how much exposure, units of radiation. So that is chapter 31. As far as we're not actually covering a lot, but there's a lot of interesting details as far as radiation therapy and things like that. So that is chapter 4, exam 5, which again is the final chapter for the semester. So the final exam will be comprehensive on all 5 chapters as far as not questions from the exam, but topics from all those. Okay, so that is Physics 1102. Hope you had a great semester. Don't forget to finish up the labs and go from there. Okay.